Yes, good evening, everyone.
Can you all raise your hand and tell them good evening?
I like this. Full of energy. Okay, so guys, we can start today's session. I am Manish Kumar here, and I'm part of the NXP India management team. And I want to share, few information. We are running NXP Campus Connect program continuously since last 2.5 years. And all the latest technologies we are sharing on this platform on every, first and third Tuesday. On first Tuesday every month, we are sharing VLSI technology related topics. And on third Tuesday every month, we are, covering the system engineering end to end, how we can enable customers related to all the technologies there. So with this, my request everyone to join and share this information with all your friends, because this is the digital platform. Anyone can join us. And since January 2023, we started this new way of, connecting with the young minds and the young innovators, that one college is going to host this session. With this, on the screen, Ashish Mittal is visible. Welcome, Ashish, for this platform. And a brief intro of Ashish is he is part of the NXP India management team. He is, all rounder, and he joined, NXP long time back. He is from, IIT BHU alumni, and having 24 plus years of experience in the different domains of SoC design lifecycle. And right now he is associated with the digital IP team. So Ashish, please share your thoughts and how, NXP India management team is going to support students to, motivate them, and sharing all the latest technologies, how they can be motivated with what is happening around us. Over to you, Ashish.
Thank you, Manish, and thank you for having this great initiative which you are doing on the behalf of NXP, and this is going to fill the gap of what we are studying in the academy and what is the need of in the industry. So, brief introduction of me, that I joined this company as a fresher. 99, I joined as a first placement, and I have a 24 years of experience in the many functional areas like SoC verification, in a mixed signal IP. I have a digital IP team, and validation and verification, tester engineering. So I have a wide experience of all VLSI function which is needed to build a chip. And coming to the VIT, I would like to thank Karthikeyan ji and Mani to come up with us, try to engage. And I would like to have a more, Manish will have a more session here. And thanks, Karthikeyan. And I think the most important thing here is that you understand what is NXP, because understand what is NXP is doing. NXP is a giant of a semiconductor. We have a monopoly in the automotive. Be it a radar, be it your infotainment, be it a body, chassis, you name anything inside.
Ashish, unmute yourself.
Yeah, Ashish.
I'm very sorry. So can
Please go ahead.
Okay. So so we have a very great legacy of Motorola and Philips, two giant companies, which are the great companies in last century, where we did a lot of innovation in semiconductor and the electronics. So NSP has that great DNA, and we are the world leader in the semiconductor innovation, semiconductor technology. And I think Manish effort and our NSP effort is going to help all different campuses, all different colleges, engineering college, where we can fill the gap. And my just one suggestion to the VIT students, that please make it interactive. Understand what is the DFT. DFT is a one function where it is required. It is very much required to have a very high quality of silicon. You must understand the DFT. So I think over to you, Manish.
Thank you, Ashish. Yes, the message is passed on very clearly that NXP India management team is committed to support you in all possible ways. And this is one of the example from our side. Thank you, Ashish, for sharing and committing and extending all the support to the college. And you are the ambassador of VIT in NXP. So thank you for all the support, Ashish.
Thank you.
Someone from the college, any professors and all, sir, share few words from your side. What is your feedback, or what type of support we can extend to enable you in this new generation requirements? VIT. Unmute yourself if someone is saying something.
Yes, sir. Sorry for the delay.
No problem, sir.
Once again, I'm Dr.
Your
Manikandan.
video is not visible. It's a blank screen coming up.
But
Please go ahead. In the meantime,
One second,
guys will correct this.
It is getting ready. So I'm Dr. Manikandan, Assistant Director of Career Development Center. So basically, our Career Development Center takes care of students' training, placements, and all industry engagements. And we are really happy, when we got this information from NXP that they wanted to do some Campus Connect activity. To be honest, as you mentioned well, especially these core companies, when they are sharing their insights well before our students coming for placements, that really add more value when they are appearing for their placements. To our students' information, I just wanted to share, NXP is one of our prime recruiter who always recruits in double digits. So really, we are very happy to have this wonderful team. And now they are taking us into a different vertical called Campus Connect. So your seniors have already missed this opportunity. That is what I have to say, because they have recruited your seniors without having these kind of interactions well before their recruitment process. If this would have happened before, really that might have added some more value during their recruitment process, not only NXP. So they are very open. They are giving this kind of insight into that core industry for all the students, right? Not only for those whom they recruited. They are giving this knowledge sharing to all our students. So we are really happy and we are very much thankful.
Thanks a lot, sir. We captured your point. Yes, we have to start something from somewhere. And, every time, someone is sharing, if I'm going to purchase a mobile after 6 months, I'm going to get a new, version which is having XYZ new features. So don't worry, sir. Everything is open nowadays. And yes, we are extending our full support.
Actually,
to your
that is a
college,
flavor of industry input, sir. Sorry to disturb. That is actual flavor of industry input.
No, thanks a lot, supporting and creating this type of, innovative culture in your university, which is helping us to, take NXP and the complete semiconductor industry to the next level. Thank you for extending full support. Yeah, we have two, expert faces visible on the screen. So first, I will introduce them. Satish Chandra, who is having 14 plus years of experience in the associate design activities. He is our expert from the MCU, MPU, which is microprocessor and microcontrollers SoC DFT part. And then Pankaj Sharma, who is again 11 plus years of experience. He is our architect in the SoC DFT and handling a lot of new technologies with respect to the microprocessor and microcontrollers. And he is our go-to person for all the complex things. So thank you guys for all your efforts, and welcome to this NXP Campus Connect platform. You see the crowd and they are eagerly waiting. I don't want to waste the time here. Over to guys. This platform is for you, in your control. Go ahead. Unmute yourself, Satish, if you're saying something.
Yeah, thanks, Manish. Thanks for the introduction.
Okay.
Good evening, everyone. Good evening, Manish. Good evening to the students and those who have joined online. I hope I'm audible.
Yes, go ahead, Satish.
Okay, so it feels good to have this platform where we can share our knowledge to the budding students and budding engineers. Yeah, so not wasting much of the time, let's directly jump into design for test. And since 1 hour is less and we have mentioned it, a deep dive, we will try to cover as much as possible. But even after today's session, I mean, feel free to connect with us, connect with people from NXP, and even you can search resources online, and you can understand this topic. I mean, it is just kind of sowing the seeds, tinkering your minds. Maybe once you have kind of interest in this field, you can definitely dig deeper. So yeah, so I'm Satish, and with me we have Pankaj Sharma, and it is designed for test, not discrete Fourier transformation. So when I was in college, I was not having this privilege to understand what is DFT, and when I got to know that I'll be working in DFT, I was thinking it is some Fourier transformation. So yeah, let's go to the next slide, Pankaj. So this is the agenda we will try to cover today. We'll start with why actually design for test is needed. What are manufacturing defects? How do we model defects? And then it's related to test, right? So whatever we design, we verify. So to verify, we call it functional verification, and design for test is different from that. So we'll try to bust this myth as well, or I'll try to differentiate how DFT is different from functional verification. Then we'll try to touch upon DFT techniques, how actually we insert design for test into the SOCs we design by covering scan methodology, tests related to memory, how we do it. I mean, BIST is built-in self-test, so there is a self-testing scheme for memory which we implement. Then there is one important protocol. I mean, JTAG, Joint Test Action Group, actually designed a protocol which IEEE eventually gave it a number 1149. So we'll touch upon JTAG and boundary scan. And finally, we will take you to the overview of AT, the testing equipment. Once the whatever we do in first two sections, we finally everything boils down to manufacturing a silicon, and then we test those silicon devices and try to figure out if there is some defective part. And yeah, so over to you, Pankaj, to the first
Okay,
section.
thanks, Satish. So we would start with the need for DFT. So good evening, everyone, in NXP Campus Connect program. And in this presentation, we'll be looking into design for test, a deep dive. So need for, go to next slides. For need for DFT, just why we need for DFT. So it is all about the test the design in your. So it is all about the finding the defect and test the design. Uh, in this typical VLSI SOC design flow. So this is the flow chart of typical design flow in VLSI. So those requirement section comes from the market, and to us, it basically comes from the marketing team of NXP. And then these requirements converted into the architectural specification. So architectural specification, then they will convert it into the functional blocks. Small or medium sized functional blocks, and we will use or reuse the IPs which may be available from the external vendor, or they might be available internally from the NXP internal IP vendors also. So those we can reuse. And in parallel to this, so let me take a pointer. So in parallel to this, when we design the functional block, our design goes to the verification. So verification, what we'll do here, we will test the functionality of the design against those specifications. So the verification will happen after the verification activity goes in parallel, and our design will go into the synthesis. So synthesis means the RTL that we have, we will convert into the technology specific cells. So we will map this RTL into the technology specific cells, and then our design will go for the physical implementation. So it will go through the layout, placement, CTS, routing, and the ST analysis will happen. So after this, our device will go to the fabrication. So fabrication means the device will go for the manufacturing. Once the design is ready, the GDS is ready, then we'll go for the manufacturing. So either it will go to any foundry, TSMC or Global Foundry. I think these two foundries, the major stakes, all the fabless company goes to these foundries. So you can see here that fabrication process is defect prone, and it can lead to faulty chips. So you can imagine the NXP basically works in the automotive and industrial applications. So here in the automotive, the stakes are very high. So we have to introduce defect-free parts to our customers, and we have to see that testability is at the level that we should not see the return part to us. So here, after this fabrication, the process in the flow chart, the process is silicon wafers. It will come, the output of that foundry will come as a wafer, and then wafer will come into the packages. So this is the typical SoC design flow. Now, where the DFT fits into this flow, actually we are everywhere, but in generally, because we are interacting, we are involved in the each stages from the architectural specification to the package part, and after the part shift to the customer, if the part return to us after many years or immediately, then also we are involved. So we are, as a DFT team, we are everywhere in this flow chart. So I'll switch to the next slide. So this is where the DFT fit in the flow. So you can see here on the top of the RTL, there are SoC specification and there are test requirements. So along with the SoC specification, we have the test requirement also. So suppose how many pins are available for the test and other requirements would be mentioned, and then we'll have the RTL. So front-end team will generate the RTL, and then it will go for the functional verification. But this RTL now would come to the DFT team also to insert various DFT infrastructure or test logic. So suppose it will insert the BIST to verify the memories in the design, and it will insert the boundary scan logic to verify the pads in the design. And if there is safety critical island in the device, then we'll have to implement the logic BIST for this. So since we work on the automotive devices, so I think these devices are safety critical, and so we have the LBIS logic for that. Now, after this, after this inserting into the RTL, our design will go into the synthesis. So synthesis means it will basically RTL will map into the technology cells, and some more basic level optimization also happen in the synthesis. Then resultant all that logic synthesis will get a gate level netlist. So gate level netlist, once we get, and these are the tools I think which are depicted. So MBIST will be inserted by some EDA tool, and the boundary scan will be inserted by BSD architecture tool. And similarly, synthesis will be done RTL compiler, or LBIST will be LBIST architect or TK hybrid. So these are the multiple vendors. You can pick any tool, but flow will remain the same. And RTL compiler nowadays, it has converted into the Janus also. So this is the next flow. So now what will happen? We have the netlist available. So in the netlist, what we'll do? We'll do the DRC analysis on that netlist. Whether so suppose we will check for the reset controllability, clock controllability, and other checks will be there, DRC checks, which we will check on this netlist. So we will evaluate whether our design is scan ready, scan insertion ready or not. So if suppose if any violation occurs in these DFT rules, then again our design will go back into the RTL mode, and we will change some logic there, and then same steps will repeat. So RTL, then we have to insert the DFT, and then again synthesis will happen. So now if we don't find any violation and all the violation are fixed, then we will start the process of scan insertion. So what is scan insertion? So scan insertion we will cover in the other slides, but I'll give you the brief here that what we'll do, we'll convert here the flop, normal flop, which has only D pin, clock pin, and a reset pin and a Q pin, will convert into that muxed flop. So we will add a mux in front of the D, so that we are converting a flop to a mux based flop. And then we will stitch the chains in a shift register, as a shift register. So we will do the scan stitching in this step, and the resultant of this scan insertion step will be a gate level netlist. So we had earlier a netlist. Now we have inserted the scan. So now we have got the scan started netlist. And now this these will go to the multiple multiple teams for the verification. So one says that the logical equivalence check we have to do. So LEC checks we have to do, whether we have to verify the RTL we have got and the netlist we have got, whether they are they are here, and piece of scanning of DFT will happen in the flow number 3. So this is the DFT flow 3. So what will happen now? We have the scan inserted netlist. So these two activities will happen in parallel. So one is the physical design. The same netlist will go to the physical design team, and same would come to us to generate the ATPG pattern. ATPG is nothing but the automatic test pattern generation. So what will happen here? We'll take the netlist and the libraries. And we would generate the pattern. We will generate the pattern, and we'll measure the coverage. That what is the coverage? So coverage targets are nowadays very high. So if suppose we do not meet the coverage requirement here, and if it is lesser than 99.3 or whatever the target we keep, then again we have to find some bug in the design, and we have to change the RTL and repeat the same process again. And in the parallel to that, the netlist will go to the physical design team, and they will perform their placement, routing, and the clock tree synthesis activity on that. And the output of those activity would be the SDF with the net delays and the netlist. So now once we meet the coverage target, and we'll have the scan vectors. Means here we'll do the GLS verification also. So we'll do the first unit level or that zero delay gate level verification on the netlist, which was available from us for the post scan insertion. The netlist was available. On that netlist, we'll verify those vectors on that netlist at zero delay. But here, since physical design also move ahead, and they have given us the timing clean netlist. So ST analysis also done, also performed on this netlist, and then we will receive it. So then again, the same activity, it will go. This output would again come here on the ATPG. Will generate the patterns, and then we'll do the simulation. And after everything is passes, including the BIST JTAG, so then our pattern are ready for the testing purpose. So these are the tools. I think tools name are immaterial here because any tool industry specific tool we can use. So basically here the FastScan is being used or test compress is used for pattern generation, and ANSI Verilog or other tools also we can use. Those are used for the simulation. Yeah, over to you, Satish.
Yeah, thank you, Pankaj. So can you go to next slide? Next. That's it. Yeah. No. Yeah. So basically, yeah, you understood the flow where DFT fit in. Now, what we are trying to achieve from design from for test. So basically, anything you manufacture can have defects. Anything in the world, and same goes for your semiconductor chips, as Pankaj was mentioning. And in mission critical situation, right, where life is at stake, when we are designing semiconductor for automotive, it becomes very very important that you don't ship a product which is having some fault. So what are the manufacturing defects? Basically, we are talking about here in semiconductor space, and how do we catch them? That is where DFT comes in. So, and when I believe you people have gone through VLSI topics in your curriculum, and you may talk to those who are in, say, first or second year may talk to your seniors, or can go to web related to the VLSI fabrication process. And you are also, while buying some product from the market, you understand, right? It is, they will say it is 5 nanometer product, it is 3 nanometer product. So it is 10 to the power minus 9, such a small thing we are talking about. And when things are so small, so miniaturized, that even a small dust particle looks bigger. And where we manufacture these things, these silicon devices, we call it Fab Lab. And Fab Lab have clean rooms. Suppose, how do we define clean rooms? Is if you go to hospital, right, they will say you take off your shoes and you wear their shoes, and then they maintain, they give you a cloth, and then you wear that, and then you can go inside. So that is also not a clean room. Semiconductor clean room is so clean that even we measure the impurities which are flowing in.
Guys, you are muted. Can you unmute yourself?
Oh, sorry. How long I've been on mute?
Just few seconds.
Okay, sorry, I don't know how I got muted. Yeah.
No problem. Go ahead.
Yeah. So basically, I was
Please
saying
share your screen. Screen is not visible.
Pankaj, can you share your screen? Is it visible now?
Yes. Go ahead.
Yeah. So manufacturing defect can come because of the impurity in the environment and what it can cause. Apart from the environmental defects, it can be introduced by the lithography. So what is lithography? So basically, we have photoresist, certain chemicals which we use for kind of to making mask, and then layer by layer making of the say active area, and then the upper layer there will be metallization, and then interconnects and vias. So yeah, so lithography, you search on web, you will find so many things. So there might be some impurity in that, or that can also cause some issue. What it will do? suppose a dust particle, it comes and it sits where you are about to say kind of make a metal line, as you see. So impurity what it will do, it will break the wire. So what we call it as a open. There can be certain impurities such that they are kind of a conductive material, and when it comes and sits between two wires which are running parallel to each other, they will accidentally short those wires, right? And definitely it will cause defect in the silicon produced. So the upper right corner in the defect is caused by the dust particles and those impurity in the environment. Because of lithography, our idea is that purely rectangular wire we are going to fabricate. But in actual, what can happen is, as you see, lower bottom. Uh, Pankaj, can you give me control?
Yeah, you have it now.
Can you enable pointer? Anyway, I believe my face is visible behind the cursor. It's okay. A pointer, it will not give me pointer. Yeah. So basically, a pure rectangular thing we are assuming as a metal stripe we will fabricate, but actually it can get fabricated like this, and because of the lithography errors, it can have some bulge where it can get shorted with the adjacent wire which is going. So all this will result into manufacturing defect. And through DFT, we are trying to and we basically we catch these defects to such a precision that we decide this is the wire, this is the inverter. You and see, it is so small, 10 to the power minus 9. I mean, nanometer we are talking about. So it is not visible even to the microscope. We need to use electron beam microscope to kind of cut it and see. So basically, where will you cut the chip? I mean, if it is a defective chip, where to look for? DFT enables that. Pankaj, can we go to the next slide? Yeah, so these are some real pictures of the defects. If you see this open, right? So basically, we were assuming that it is connected, and because of say lithography issues, it remained open. So definitely, it will result into a functionally bad behavior. I mean, it will not work as intended. And this is a zoomed area of this. I mean, there are two adjacent wires which are not supposed to be connected, and they are actually getting shorted. So it can result. I mean, your functionality will no longer be available through this IC, right? And it can cause multiple issues. And to catch those issues, catch those manufacturing defects in terms of electrical parameters, we call it modeling and precisely fault modeling. We'll come to that as well. What is VIA? Those having the understanding of VLSI will understand. Otherwise, when I mean, VLSI manufacturing process is like through stencils, and we call it masks. And layer by layer, we have multiple layer of metallization. So a plain device, one thing needs a connection to the other thing. Can happen to layer one or to layer two or layer three. And to do this connectivity, we dig a hole. It's like a well structure, and that well is called via. So ideally, the via should be round and I mean, its shape you see, right? It's a cylindrical shape, but it can have manufacturing defects which can look like this. And what it will cause? It will cause a change of resistance, and which will eventually turn into delays. And if it is broken, it will be detected as open. And uh, all in all, we want to detect it. We don't we I mean, how we are different from verification. The slide is coming, but just as in we can see the defects. Just to cover, we are trying to catch the defects and catch the defects very early, such that it doesn't go into field or it doesn't do harm. Can we go to the next slide? So what are now we understand that there are issues in manufacturing, what they will cause. So they can basically we will categorize them into three categories. They can either cause functional issues. That means your device is supposed to do a functionality A, but it is not doing it. It can cause speed defects. Speed defects as in it is still working the way you wanted, but not at the frequency which you want. For example, you designed something to work at 1 gigahertz. Now it is not working at 1 gigahertz, but it can be operated at 0.5 gigahertz. So, I mean, you'll lose some market, some applications, or it is not used for you, right? You wanted the device to function at 1 gigahertz. Leakage defects is it is manufactured good, working fine. Speed is also okay, but it is draining out your battery, right? And why it can so functional defect? I mean, open shorts cause the function defects, and speed is I mean some resistive path or malfunctioned vias will cause the speed defects, and leakage defects is you have a path between VDD to ground shorted. I mean some defect in transistor somewhere causing VDD to ground to be connected, and your device is losing or consuming power. And if it is a battery operated device, I mean it will not be. I mean it will take out juice of the battery very soon. Yeah. Next slide, please. So basically, how do we screen defects? I mean, fundamentally, if we were not presenting DFT to you, I mean, you could also think of something like you want to catch defect. Okay, let's apply some stimulus. Stimulus means let's give some known input where we understand what should be the output response. I mean, you give inverter input on the input side 1 and you expect a 0 on the output. So similarly, you apply a stimulus, you measure a response, and you know what is the expected response. And the stimulus should be chosen such that you can differentiate between good and bad behavior. For example, you need to choose your input carefully such that two different inputs should produce two different outputs, and those two different outputs should be pointing to some specific fault. And when you compare the output with expected output, if it is mismatching, then you understand, okay, there is some fault. How do we dig deep and go directly to the fault? We do it by cycle behavior. So in our DFT, Pankaj anyway will cover how scan chain looks like and how we load the data, how we unload it. So basically, every pattern along with the every stimulus along with the expected data with cycle will give us a view that okay, what is actually faulty. So something failing, we can take that pattern and we can pin with a pinpoint accuracy. We can say, okay, this is the area, this is where the fault looks like, and sometimes through logical evaluation, we get okay. Here the timing was not met, or the timing was meeting at very edge, and this can be susceptible to the changes, or it can go to the failure analysis where post silicon things come into picture where you can itch the device, or you can cut it, or you through electron beam microscope you can go and really see why all this is required. Because you did everything right. You didn't wanted this manufacturing defect to be there, and despite everything, if something is faulty, you want to correct it, right? And since you knew that all the processes, all the checklists were followed, still there is some defect. So with pinpoint accuracy, if we are going to tell, okay, here is the defect, then you can go back and see how you can fix it. That is the greater aspect of it. And on the first hand, what you can do is defective IC. You can throw it such that it doesn't go to customer or doesn't create a big harm. Can we go to the next slide, please? So basically modeling. So we talked about defects, right? Now the question is how we are with the accuracy saying that okay, this is stuck, this is open, this is bridge, this is delay, right? So definitely we should model it. Manufacturing defects needs to be modeled in some electrical manifestation. So don't get confused by this complex English. I mean, it's like you have a defect and you want to create a stimulus on the input side so that you can, with the electrical way, that means if an inverter is faulty, where input of the inverter is always tied to 1, so your output will always be 0. So if you give input, if you try to give input to the inverter as 0, it will still be at 0. Output should be going to 1, but it will not go to 1. So that kind of modeling we have to do, and through the scan techniques, and we will be then able to clearly say, okay, this has gone faulty. So we have different types of models which detect different types of things. For example, we have stuck at models. So by the name it goes, right? Stuck at, it is stuck at 1, it is stuck at 0. That means for some reason, because of manufacturing defect, your wire is tied to VDD. It is even if you try to drive a 0 through that wire, it will never get a 0 because it is tied to 1. So those are stuck at faults. Then you have transition faults. That means it is not stuck at, but it is not as fast as it should be. I mean, it is slow. Then path delay faults. I mean, things are fine in isolation, but if you look at a path, you find it there is a fault. Then bridging faults is there are two wires which are going adjacent to each other, and you drive a one in one wire. The other one is not connected to it, but still it changes a value, right? So driving value on one of the wire changes value on the adjacent wire. And then memory faults and IDDQ fault. IDDQ fault is, I mean, basically um, in your steady state, nothing. I mean, your device is sitting idle and it is draining current. Ideally, it should not draw that much current. So we model all these types of faults. Why we model it? So that we give a stimulus, and when we measure output, then we can say, okay, it is stuck, it is delayed, it is having a path delay fault, its memory is having some issue, it is got a big leakage, right? So this OR gate which you see right here, I mean, basically, if I try to show you what kind of stuck-at faults it can have, so it can have basically 6 stuck-at faults, right? This A input can either be stuck at 1, it can, because of manufacturing defect, it can be tied to say VDD, or it can be tied to ground, right? So it can have 2 faults, stuck at 0 on A, stuck at 1 on A. Similarly, at B, you will have similar 2 faults. And similarly, at the output, it can get stuck at 0 or it can get stuck at 1. So basically, now when we say how many faults in the stuck at type of modeling it can have 6 types of faults. Can we go to the next slide, Pankaj? Similarly, if same OR gate has say delay faults, so we are here modeling the defects, right? We talked about manufacturing defects, and now we are trying to model. Okay, so what if this wire is intact but it is slow? So it will have either slow to rise or slow to fall. I mean, definitely there will be 2 paths rise. For rise, you will have PMOS coming into picture. For fall, you will have NMOS coming into picture. So it can have slow to rise, slow to fall, or B can be having a issue where it is, I mean, slow to rise means to go from 0 to 1, it is delayed, or slow to fall means from going 1 to 0, it is delayed. Same on the output side. So basically, we can have 6 types of transition faults. So there will be many names to the transition faults. If you call it TD, if you call it transition delays, if you call it AC faults. What it will do, for example, something was supposed to get down to 0 here, and since it is having slow to fall, it is getting delayed, right? And how it will get caught? Basically, there is setup time, right? So if there is additional delay in this circuitry, what it will do, it was supposed to catch a 0. but it will come near to clock, it will catch a 1, and this 1 on the output for a particular pattern will tell, okay, there is some issue with the delay. Can we go to the next slide? Yeah, so similarly, if there is some manufacturing defect in PMOS, how we are going to catch it? So basically, we are this inverter, we are giving a 1, and when we give it a 1, this NMOS will be on, and output is supposed to be remain at 0. What will happen? This defect where source and drain is shorted, what will happen is a huge amount of current will be going from VDD to ground, and through IDDQ or through the current measurement, we will definitely catch it. Bridging fault is like, I mean, as discussed earlier, I mean, you drive one value here, it influences value on the other wire. So, and once you catch through this wire, you know you are not driving. If suppose this wire it was supposed to be at 0, you drive a 1 wire here, and if you catch a 1 from here, you know, okay, there is some bridge defect happening. And why it can happen? I mean, because it is so miniaturized in the nanometer regime that these kinds of issues might happen. And through DFT, I mean, once we give you in a pinpointed way, okay, here is the issue, then the corrective measures can be taken at various places, whether it is correction of a library, whether it is correction of mask or process or say logic or whatever. Can we go to next slide? So yeah, so why to focus on test? This is very exciting. So basically, the early you catch it, the less loss you have to bear. So during the IC design process, that means it is still not manufactured. You catch a defect. That means your PNR team thinks that the timing is met, but when you run your patterns, you find okay, it is not met. That means some man hours will go, but you will eventually correct it. So the impact is very less. It is manufactured, and then through your test you are getting it. Then you have to throw the silicon. So of course your cost is increasing by factor of 10. It is just, I mean, a random rule. I mean, somewhere like Moore's law, it is kind of holding. So it is becoming a factor of 10 rule. During final test, when it is packaged and standalone IC, I mean, it is not caught on wafer, but you are catching those packed ICs, and you have to throw them by you identified defect, and you have to throw. Your cost, of course, increases. If you catch it at board level, it went, and it once you fit into board, and then you catch the defect, of course, and finally when it is in system and it is fit into the car and your car doesn't start, and then you come to know that there was some issue, right? So the early defect you catch, less price you have to pay. Next slide, please. Of course, nothing comes for free, right? So even DFT has some impact on the cost. If the DFT or designed for test influences your device cost, of course, we are not kind of driving the functionality, but we are there to catch the defects. But once you implement DFT, your cost increases, but your competitiveness also increases. So one SoC having a good DFT or with or without DFT, of course, people will choose tested IC, right? So their competitiveness wise, it gives you an edge. Tester cost is high. It comes, I mean, with the amount of time you use tester, it increases cost. So the more thoroughly you test, more test time is required, and hence the cost increases. And with technology growing means things are getting miniaturized. Transistor size is decreasing. More and more transistors we are packing into same area. That means in greater number of test patterns will come into picture, which will result in more test time, and hence the cost will increase. Yeah, next slide, please. Why can't we use functional test? Anyway, we are AND gate. We can write 00011011 and we can verify, right? But when we are talking about millions of transistors put within a very small area, through functional verification, you can, it will take ages. It will take so much long time to kind of find run everything and then find an issue. And you assume you have to manufacture tens of thousands of such chips and you have to ship it to the market. So I'll go fast. Time is running. So basically, there are two ways we are better. One is through functional verification. You cannot test everything within specified amount of time. If you want to do, your cost will be so huge that it will be unsellable. With the DFT, your patterns are very small. So if you see the columns, right, you need all these vectors to test something functionally. Your vectors are very small when you go with Stuckit. But so to give you another perspective to it, a 4-bit counter can take 2 raised to the 4 to the power 4 patterns to verify. That means functional verification. But it needs only 8 patterns for structural testing. So you see, we are better. And functional verification, even if you are able to verify something through functional patterns that okay, it is faulty, you are just verifying it is faulty, you can throw it. But it doesn't give you a view. Okay, why it was faulty? Where is the fault? What to be corrected such that the next lot of chip doesn't have this faults. So right. So DFT has an edge over there. Next slide, please. Of course, few more points. Functional versus DFT. Anyway, I've covered. So functional tests, you verify the correctness. Automation is not there. DFT gives you debug feature. You ramp up to the volume production is very fast. That means cut. Yeah, so many ICs. You can test it in very short span of time with very small number of patterns. Can we go to the next slide? What all does DFT do? So basically, this is a summary. Anyway, next slides we'll be covering how DFT and BIST verification is done. So D presides the T. This is, design is involved in test, right? So it is designed for test, and design takes the center stage where you suppose we are inserting a design on top of the functional design to enable the testing. How it helps? It helps in exhaustive testing through scan. It helps in kind of diagnostics through memory based and built-in self-test. Built-in self-test is, even if your device is in field, that means when you switch on your car, there are certain tests which your SoCs goes through, and if something is faulty, your dashboard kinds of blinks something. Okay, your airbag is not working or whatever, such that you can take the corrective measure, right? So it is built-in self-test in field. It through DFT, critical IPs can be tested, which are embedded inside. For example, there is some analog block which is sitting deep inside your SoC. DFT through DFT, you get a expose mechanism such that you can visualize what is happening or how this analog IC is functioning through the expose mechanism, so such that the input and output can be ported on the very output pad. Debug and corrective features, for example, in memory repair and diagnostics. So we kind of through DFT, you can correct your memories. For example, you found out that okay, this row or this column or there is a fault in the memory. You can correct it. To a certain extent, right? So that diagnostic capability also comes through DFT. Test time optimization. So basically, as we discussed, right, it is very costly, and as chips are getting more denser, the test time is increasing. So there are kind of efforts on the design side of DFT as well to reduce the cost, right? So scan compression and other methodologies are there, and it gives you standard mode configuration like JTAG, where other manufacturers who are manufacturing SoCs, if they are compliant to JTAG, right? So through that compliant features, you can onboard, you can test the interconnectivity and all that. Can we go to the next slide? Yeah, so over to Pankaj for DFT scan techniques.
Okay, thanks, Satish. So the various DFT techniques are present to test the design. So let's consider a very simple circuit to understand the stuck-at testing. So here the two AND gate and one OR gate, and all those inputs are driven by the primary input, and output is observed at the primary output. So these are the primary input and these are the primary output. So in order to get the full controllability and observability, I should be able to drive either 0 or 1 on all these nodes, A, B of U1 and AB of U2 and AB of U3. So if the fault are not present in the circuit, then the output can never be driven to 1 due to stuck at 0. Due to stuck at 0 at B. So if suppose if I apply a pattern and I get stuck at 0 here, then if I get the value 1, then I cannot able to propagate that. So if we see here, so what I want to do in order to test this, first I'll activate the false side while driving the opposite value. So since here I found the stuck at 0, then I'll drive the opposite value from the primary input, and I can see I'll try to observe that at the output port, at the primary output port, because at the internal node I do not have the observability. I can only see through the primary output port. So if I want to propagate that 1 to here, then I have to drive A input of U2 to 1, and I would need 1 value here to pass through this logic to the output. So I would need either 1 or here I can use the 1 or X, so whatever the value is there. So you can see the correct response I'm supposed to get, that is 1, but I'm getting here 0 because this fault we have got is this node. So the first we will activate the fault side by driving the opposite value. Second one will be propagate the error to the primary output while applying the primary inputs and the value at the primary inputs. And then we can compare the fault with the free value. So if suppose if we get 1 and the expected also 1, then there is no fault, stuck at fault here, but suppose here we are getting the opposite value, it means that we have detected the stuck at fault here. Now, the how to test millions of internal nodes in a large SoC, because the previous example I have taken a small circuit, but we have the millions of such internal nodes in a large SoC, and we cannot observe everything at the port. So first option, we have to expose all internal nodes to the primary inputs and output. So this is not efficient, and it will have the multiple design challenges. So what is the other option we have? So other option we have that primary. So we can consider the fact that all nodes are driven by either primary input or flip-flops. So with some design modification, the state of internal flops can be controlled. So what are these design modifications? So this is a flop. It has input D. It has a clock, reset, and output Q. So this during the scan insertion, what happens that this flop is converted into this circuit. So what we have here, so we have the D input of the flop, and we have added a mux where the two more inputs have been added here. So one is the scan data, and another one is the scan enable pin. So here you see this. This is we have converted a normal flop into a scannable flop, and now we are what we are going to do in the scanning session. We are stitching those flop into a shift register. So after the scanning session, you can see these flop we have converted into the scannable flop, and we have stitched these through a shift register. So one primary input scan in is added and one scan out, and another is the to control between the test shift and the capture mode. We have added a pin called scan enable. So how we'll catch the defect here in the shift mode. We'll load the value from this pin. So since the scan enable is 1, then the scanning the pin will be selected and it will shift out the value from here. So during this when the scan enable is 0, we call it the shift mode. Shift mode, the SE is asserted to logic 1 and flops are connected serially as a shift register. Now, when the capture modes, when we are in the capture mode, then shift enable goes to the logic 0 and functional path gets activated. So now we'll capture the response from this combination cloud. So let's see this. First, I will drive the value first clock pulse, second clock pulse, third clock pulse. So all the values are getting loaded here. So 101 are getting loaded here. Now we are into the capture mode. So capture mode, now the response would come, the combo response would come from here. So it has come to 0 now. So now we'll give another pulse and then we will shift out the data from here. So if suppose those value does not match with the shift in data, then at the shift out, we will get to know that this device is defective. And we can, after the shift out, we'll get to know that our pattern has failed and we can throw that device. And these are the port requirements. So scan data, the pin is required. So one pin is required based on the internal chains which we have. These data pin can vary upon based on the size of the design. So one scan out data pin is required and one scan enable pin is required. So that is to get the design into the shift and capture mode. Now, with respect to the transition fault, so suppose if we have the transition fault, the slow to rise or slow to fault in our design, then what would happen that suppose this is the launch edge and this is the capture edge, this is the launch and the capture flop, and this is the launch pulse and the capture pulse. So this is the good part in the mentioned in the dotted line. So suppose if I've launched the data and I want to capture the transition, then I should be able to capture the transition here. So this is my capture edge, and I should be able to capture the transition here, one here. But what happens if it has more delay? Then I won't be able to capture the transition on time. So it will resultant into the transition fault. So this is the transition fault. Again, this is the same circuit, but now the things will change here because this is the same combo cloud. The shifting is desired. The shift in the means will shifting the desired logic from this pin, and we are shifting in the desired logic from this pin, and we will launch to generate the transition event. So I should be able to generate a transition. I should be able to generate the transition here. You can see when I'm in the capture mode. When I'm in the capture mode, you can see from the combo cloud, the response is coming out to be 0. So now in order to, so we have to launch the transition to generate, we have to launch it. So we'll give a launch pulse and then response will be captured here. The transition will be captured at the capture pulse here. So then we can shift out the data and we can, you would have observed here, first I have shifted the 101 here, and then this here is the launch pulse 1 and 0. Means one, first here it was 101. Now at the when we have given the launch pulse, then 0 would come from the combo logic to this Q pin, and then at the capture phase. So you can see here these two, the transition, transition fault we are getting in this 1 to 0. So means 1 to 0 transition and 0 to 1 in these two flop is happening, this transition. And then we can shift out the data to know whether it has passed in the time or not. So now let's, so these are all about the transition and the stucket fault. The transition fault, also called all the delay fault. And now let's see through the what is the coverage. So fault coverage and the test coverage. So coverage provides the metric to determine in terms of percentage how many faults under design can be tested by a single pattern. So fault coverage is number of detected fault upon total number of faults. So means I have shown an example. Satish has shown an example of an OR gate. So it has total number of faults. We have 6 total number of faults. And if 2 are or 3 are detected, then the fault coverage will become the 50%. And if all 6 are detected by test pattern, then our fault coverage will become 100%. And the test coverage, what is the test coverage? So the formula is similar, but in the denominator, what we are doing, we are from the total number of faults, we are removing the untestable faults. So untestable faults are nothing but those cannot be tested. Those cannot be tested. They can either can be used unused fault or the tied. They are tied inside the design, or they are not being used. Suppose the Q bar is not being used, so that is the unused port. And if suppose any tied is there in the design, so those are the those comes at a untestable faults. So for our SOC, we consider the test coverage because if you can see that we are subtracting from the denominator, so obviously the test coverage would become higher. So we consider the test coverage for sign off. Now the other DFT techniques are the memory based. So since the memories are there in the design, and this is the memory cell array. They are based on the matrix. So there are a column decoder and the row decoder is there. And then these are chip enabled, the control signals are coming, and the data is coming out to be here. So all the control signals are will apply here, and and we can do the read and write operation. So this is the basic the block diagram of a RAM. And then this is the memory bit cell. So it has the 6 transistor SRAM. So These are the back-to-back transition coupled. It will act as a storage device, and these are the BLs. So it will provide the control. So each bit is stored in a cell composed of several transistors. So this back-to-back the coupled the back-to-back transition will store the data, and these will act as a control logic for the memories. And for the memory defects and the faults, so these are the various type of faults that we cover through the memory testing. So stuck-at fault, transition faults. So these are similar, which I have already covered. Satish already covered it. And then apart from this, the dry destructive fault. So suppose if a non-transition write operation is causing causing a memory bit to fail in transition into the opposite state. And then we have the read destructive fault. So in the read operation disturb the memory bit. And then we have the address decoder fault. So suppose fault in a particular this address decoder logic and means we prevent or cause the data to be fetched from a wrong address. And then we have the coupling fault. So due to the coupling fault, the existing cell transistor can cause the victim cell states to be changed. Then we have a bridging fault, which can be caused and neighborhood fault. So this is also these are the affected by a neighbor cells. So the values on those cells because of neighbor cell can be changed because the structure inside memory is very complex. So they are just sitting close to each other. Means the memory defects and faults are more than this, but this is just an example to understand the basic faults around the memory. And this is the March algorithm. So algorithm we use for the memory testing is called the March algorithm. So this is a sequence of read and write operation. The applied consecutively on the certain memory cells before proceeding to the next one. So here you can see here this M0 is the March the sequence and March sequence here the R0 and R1 is the read 0 and read 1. W0, W1, write 1 and write 0 and write 1 operation. Here this and the top arrow it is indicating that the memory is being written in increasing order and the lower arrow shows it is written in the decreasing and this when the cap is there on the both side then it is the address order means it is irrelevant. Either it can write means both increasing order and decreasing order. Both it can be it is data. It can be written in the both the order. So in the March 0, you can see here this is the first step, and this write 0 is happening. Means the write 0 is happening in the increasing and decreasing order. And in the second March step, when we have written 0, we are reading it 1 and writing it back again. Sorry, we are reading is 0 and writing it back again 1. And this is the third step. So now we are here, we were reading into the incremental order. Now in the M2 step, the March step, we will read into the decreasing order. So we will read 1 and write 0. So this is the block diagram of a memory. Here we have the memory address line and the data line and the control signal. So basically any memory will have address, data and control signals. So these here we have depicted the BIST caller. So BIST caller it will have a MUX implementation. So either the address, data, and control signal can come from the functional logic, or they can come from the test logic. So you can see the BIST mode is there. So here, when this BIST mode is 0, then the functional path would be selected and the address, data, and control will come through the functional path. And this logic we have inserted in our design to test the memories. So the test pattern generator block, test controller, and the comparator blocks are there to capture the response. Comparator is there, and to control signal, the test controller is there, and this is the address and data generator is there. So when BIST mode is 1, then data would come from this block. This block, this BIST controller is there. So data would come from this block, and in the function mode, it would come through the function path. So since this is the built-in logic, this device, this logic is present inside the device, and we can generate the multiple March algorithm to test the memories based on the technology nodes. So algorithm sizes and type of algorithm will change based on the technology, the technology the the memory is working on which technology. Over to you, Satish.
Yeah, thanks, Pankaj. So basically now you've seen that you can insert DFT functionality through scanned, and memories can be tested with BIST. Now, question is, if you have two SOCs which are internally can be tested through DFT techniques, but now these SOCs are present on the board and they are kind of sitting parallel to each other on the board. So how do you test the board connectivity? Whether on the board also, I mean, there are connections, right? And the green color board you see, right? Wires are going and joining two chips on board. So we have another technique which can be while manufacturing the SOCs. If we make them JTAG compliant, we can test the connectivity at board level. Also, this JTAG technique helps in testing and mode entry inside the SOC. So here we are focusing on the board level. Can we go to the next slide, please? Yeah. So a little bit history of it. So basically, JTAG stands for Joint Test Action Group, and in mid 80s, it was I mean, people were finding it difficult. I mean, different vendors were implementing different types of techniques to test the SOCs from inside. But once you put them on board and you want to test the connectivity, there was no standard way, and then people created a group called Joint Test Action Group, and created a methodology where through a 16 state machine there is a protocol for TAP protocol, and through which this testing can be possible. IEEE adopted this and gave it a number 1114.1 for digital testing, and 1149.6 for analog. Can you go to the next slide? Next slide. Yeah. So basically, no, previous one. Yeah. So basically, what happens is we have a boundary scan cell, and on this greener side, you see a boundary scan cell, and this chip pad is written, right? This is a chip pad. So basically, this is the port which comes out, and it is visible to your eyes, and through it connectivity happens. But on a board, can you go 2 slides next, Pankaj? Next slide. On a board, you see that there can be a board where there are multiple SoCs having some connection, and you really want to test, okay, things are properly working within this chip, or you want to test, okay, the connection between this and this is happening fine or not. So there it required a protocol through JTAG. It can be enabled, and you assume that every port, behind every port there is a specific cell sitting which is making all this happen, and that is called boundary scan cell. Can we go back to the same slide, Pankaj? Yeah, so basically behind every pad you see there is a special cell sitting which is called boundary scan cell, having three muxes and two flops. Basically, you can divide it vertically. So what happens is, suppose below this pad you have another pad, above this pad you have a pad, and similarly the BSR cells are every pad is having a BSR cell as well. So once you are not in BSR mode, that means chip is not, I mean, we are doing normal functionality, we are not testing it. So this functional input goes through the pad, and it goes to the outside world, and it works in the intentional way. But now when you want to test it, so that means you are in now BSR mode, and then this path becomes active. What it gives you is through X-test mode and shift DR, you can load data. I mean, you assume it will all be a series of shift registers, hence it is called a shift DR. So above this, another BSR cell will come whose this flop shift register will be there. So it will kind of create a shift register. You can load it the way similar to what Pankaj has shown as a scan chain. Once it is loaded, then it can be unloaded. It can be loaded on the update register through the 16 state machine, and that data can go out. Can we go to the next slide? So you see here, I mean, tap controller is sitting, and the beauty of this protocol is basically with minimum set of pins, you can achieve testing of a board uh, along with isolating one of the SoC and testing it. So this tap controller protocol works on five maximum five pins, which is having one input TDI, one output TDO, one for clock TCK, one for mode selection TMS, and one for reset. Again, you can leave reset as well, and this protocol still can work with four pins, omitting reset. How do you do reset then? You make TMS 1 and give 4 clock cycles. It will do the reset. So this boundary, the entire boundary you see, right? They are the BSR cells, and how it is connected. Can we go to the next slide? So yeah, so basically what happens is this JTAG is kind of providing a mechanism. You want to test this connectivity, or you want to load a one here. You give a one key, start shifting. One reaches here. This goes into in test mode, and then you shift out and you take out the data. So it kind of gives you a controllability to all the SoCs present on your uh, board. And this JTAG protocol also assists us in the mode entry scheme. So it is present inside also, and with a similar way, there are TDRs. I mean, on this boundary, these cells are boundary scan cells. Inside there can be test data registers which can be loaded through JTAG, and we can enter into. So whatever static values we want to give in the test, for example, as Pankaj was just discussing about memory BIST. So you want to enable BIST, you want to disable BIST. That means you need to have some static values. You want to program them such that the device enters into that mode. So this JTAG helps in that as well. So diving it will be taking more time, so it is getting out of scope. So basically, this is we are trying to give you a thread, and you can go and dig deep and understand more. Can we go to the next slide, Pankaj? Yeah, over to you, Pankaj.
Yeah, okay. So this is the final section, the tester overview. So what happens? So this is the pass flow. After the fabrication, what happens that the wafer comes, and then we do the testing of those wafers, and we get the pass fail result. And then what happens that whatever the passing wafer is there, then means then we will ink them. So the inking process will happen, whichever has passed the vectors which we have given, and then it would come out as a good chips. And then this is the automated test equipment. So this is the wafer is there on the prober, and this is the mainframe where the patterns are being loaded. And it has the memory and the computing logic inside this mainframe, and this has the console, so it will have the keyboard and the display. And this is the prover. So when the wafer comes out of the fab, then the prover will be around the wafer, and test head is there to test each die in the wafer. So when you're seeing here, these all are the individual die combined into wafer. Prover is there on the wafer, and these are the test head. The test head is going into the each device and testing it. And after this, the testing happens. So whatever the good devices comes out of this testing, they go for the packaging. So directly, why we are not going for the packaging? Because during this testing also, during the probe testing, we are saving the cost of the packages. Because suppose if the Satish has shown you the rule of 10. So suppose if we catch the defect here after the package part, then the cost would increase than the for the company. So what happens that we do the testing at the probe, and then once the final we do the packaging, and then after packaging also we do the testing using the same equipment. AT is there. So the test pattern will be generated. This using this logic, the memory is there, the computing logic is there, and these are the test head. Uh, so, so this is the tester flow. So we do the testing at the probe and the package level. So this is this is the Teradyne tester diagram. So this is a big device. It won't fit into a single room also. And this is our last topic of our presentation. So this yield and DPPM. So yield is called the fraction of good chips produced during the manufacturing. So if the yield, we want to get a higher yield, then we should roll into the good chips during the manufacturing process. So, so if the yield is higher, so means the fabrication is good, or the test program is good, then everything is running as per our expectation, and the yield is dropped, then there could be multiple factors. Then there could be an issue with the fabrication process, and then could be a test program issue, and might be the external the other issue also happens. And the DPPM, so these are the defective parts per million. So DPPM can only be measured using the customer returns. So we have the policy to now the NXP is moving from PPM to the BPM. So these are the parts per million, and now parts per billion. customer returns if it is a minimum power. So if we generally have 1 or 2 DPPM parts. So if it is more than this, then I think we have to improve our process. We have to improve our design to go effectively. So I think with this, the end of the presentation.